Good morning, everybody. I hope you can all hear me. Can someone give me a sign if they hear me?
Yes, we can hear you.
Yes, I can hear you just fine.
Great, thank you very much. Welcome to this CSM tutorial, 100% remote tutorial. It's the first time that we do this. As you know, it's going to be 100% over Zoom, but with the links that we're using today, it's going to be the same link for the entire week. My name is Gunther Legui. You have heard from me via communication letters or individually when you had questions. I'm chairing this tutorial committee this year. I am a project scientist at NCAR. I'm an ice sheet modeler. I work in the polar and paleoclimate group. And I'm also the scientific liaison of the Land Ice Working Group. So this short welcome talk is just going to go through some logistics again and talk about inclusion here at NCAR. Oops. So typically, when we have the in-person tutorial, it takes place at the Mesa Lab in Boulder, which looks like this. And obviously, we're not there today, unfortunately. I wish we could. It's much better to have in-person meeting for the tutorial. But we hope that we can see you there in the near future after the tutorial. And to give you a sense right now, because of COVID, not many NCAR staff are actually at the Mesa Lab, and just like me, you can see my background. We all work from home, and we are all doing this tutorial from home. Besides a handful of us, Elizabeth Faircloth is at the Mesa Lab right now to manage the logistics of this call. I would like to give some thanks for all the people that were helped in making this tutorial possible over Zoom. First, the tutorial organizing committee, Alice Duvivier, Cécile Anet, Gustavo Marquez, Keith Olson, Adam Phillips, and Christine Shield. You will meet every single one of them throughout the course of the week. But also very, very thankful for Elizabeth Faircloth and all the logistics support that she's done to make this possible. The National Science Foundation to support our salaries and fund and making this possible. Our computing supports, Rory Kelly, who created your account on Cheyenne and grouped and linked your project code if you already had an account, but also Mark Moore for the software insights that he provided. Ryan Johnson, who made the website and is helping with the broadcast of this tutorial, but also all the speakers, helpers, and developers. It took about over 60 staff, NCAR staff, to make this tutorial possible this year, and you'll meet 45 of them throughout the week. And I also like to thank you, the participants, because you are the first generation of taking this tutorial online. Hopefully it will go very well. Hopefully you will like it, and hopefully you will learn a lot. And I know it's not going to replace the in-person tutorial, but we'll do our best, and I hope you'll enjoy it. As I said, this entire meeting is over Zoom, and I'm going to let Elizabeth Faircloth talk a little bit about Zoom so that we all start on the same page. Elizabeth.
Good morning and welcome, everyone. As Gunter said, I am in the Mesa Lab today, and it's pretty quiet up here, and we do wish that you were all here. So I know a lot of classes and meetings have been happening remotely over Zoom, but we don't want to assume that you're familiar with the Zoom tools. So I'm just going to take a minute to go through some of the kind of ground rules. If you move your mouse over the bottom, you'll see a black bar that gives you a lot of different tools. And so we'll use that chat function quite a bit down at the bottom. Also, depending on how many times you've used Zoom or how your account is set up, sometimes it comes up with a really crazy name. And so when you scroll over the participant list and find your name, there's a blue button that says more. And if you could please rename yourself. I will be monitoring since we're using the same link the whole time. We want to make sure that it's just the participants and the staff that are involved. And this knowing that I see your name, it lets me know that you're there, and any other people I can boot them out. So if at some times during the agenda, we're going to be working in some small groups. And so if you're having any issue with code, we might ask you to share your screen. So that would be the bottom, that green button at the bottom. And then also during the presentations, we ask that you keep yourself muted and your video off. We'll ask you to put your video on when we're having some group discussions. That way we can see each other and interact as best we can in this remote environment. But we've just found when there's scientific presentations going on, if you keep your video off, it's less distracting for everyone else. Can you go to the next slide, Gunter? So here's some additional tools. We're going to be using the chat quite a bit to ask questions. If you see in the image where it's got that blue oval that says everyone, that allows you to just post a general question. If you have some kind of technical or logistical question, you can choose me and write just to me, and I can help you. And I'll also be monitoring my email if you have some kind of logistical questions you need to send over. And then also in the participants list, you can see everyone's name, and then you can also use this if you really have a more longer detailed question that's too long to write out in the chat. You can raise your hand when we've got some question and answer sessions. Okay, next slide. And during the agenda, especially in the afternoon sessions, we're going to be using breakout rooms quite a bit. So this is, we think that it's really fun. We use it a lot here with our committee meetings. And so we'll be dividing you into breakout rooms. And this just shows you a little bit of what it looks like when we send you off to your breakout rooms. And there's also a button in the right-hand corner. This allows you to leave the breakout room and go back to the main room, or you can leave the meeting altogether. And as Gunter said, we're using that same Zoom link the whole week to make it easier for you so that you can come and go, or you can stay on the whole time, and the scientists can come and go, and I'll be on the whole time in case there's questions or logistical issues. But we wanted to do that to make that easier for you. Okay, next slide. There we go. So thank you again, and I look forward to working with you this week.
Thanks, Elizabeth. So I'm going to share some ground rules that we observe here at NCOR and UCOR, and whether we are in person or over Zoom, like this Zoom is a NCOR link, and so the NCOR and UCOR rules apply. I would like you to know that when commenting, asking a question, presenting, or simply communicating, please, be respectful. Please offer constructive feedback. Share the air with everybody. Like, don't monopolize the conversation. Acknowledge your teamwork. Encourage innovation. Show appreciation. Consider new ideas. All of this very helps making a very welcoming and encouraging environment. So, you know some logistics now. You know most likely now about the CESM tutorial website. There's a link of the 2020 webpage. You can see all the previous webpage from previous tutorials. And I forgot to say this, but all these slides will be posted online at that link, and I will show several other links so you have access to them. And if you need any other links like the agenda or special announcement, I'm not sure there's anything there yet, but the participants list where you can see the biographies of the participant participating this year, all these links are here. And if they're not there, they will be there. They will be soon. Now, a typical day typically an in-person tutorial starts at 8:30 and ends at 5. Because of Zoom, we have a lighter version of this. And what's going to look like, besides on with slight modification on Monday and Fridays, every morning there's going to be a question and answer panel session, which will be recorded and posted online on the coursework tutorial. This Q&A session is not meant to replace the videos that you might have watched already, but they're meant to ask questions and get the answer from the experts that have volunteered to participate. So then you're gonna have a Meet a Scientist session, except today. The Meet a Scientist is replaced with a Q&A panel session, and the Q&A panel session is replaced by a lecture today, where you will be meeting with not necessarily NCAR scientists. There's going to be scientists from other institutions that are collaborators or co-chairs of NCAR working groups. And there's going to be 10-minute breaks after each session. At lunch, what we call lunch, that's going to start at 11, we're going to give you the possibility to meet among each other participants. Typically, during the in-person tutorial, you guys would have the opportunity to have lunch together, to go on hikes together, to socialize in the evening together. It's going to be harder to do this on Zoom, but we wanted to give you the space to be able to do this. So we can send you into breakout rooms during this time. You can have lunch there. And you don't have to, but we highly encourage you to. In the afternoon, we're going to have the office hours, and I will get into more details about the office hours. So about the Q&A panel sessions, as I said, they will be recorded. As Elizabeth said, please mute yourself during the session. If you have a question, whether during the panel or at the end, please raise your hand, and the moderator will give you the floor to ask your question. As you might have noticed in one of the communication letters that we sent you links to pre-ask some questions to the panel. Those links are still up and running if you have not done so yet. It might be a little bit late for the atmospheric Q&A session, which will take place this morning. But you will still be able to ask a question when the time comes. But please keep asking your question for the remaining of the week for those different sessions. Meet a scientist. So this is your time with a scientist, and there is no agenda. So whatever the outcome of this session is really up to you. Try to obtain the information you came looking for. Those are not recorded. They will not be put online. And here, the exception is unmute yourself during the session. You're allowed to talk, but please try to avoid background noise and to not overspeak on top of each other. Follow the guideline of the scientist. If the scientist asks you to do something, please do it. You can check your scientist assignment for each day. It's posted online. And please do not monopolize the conversation and let everyone have a turn. There's going to be up to 6 participants with each scientist, and everybody would like to have some information. If you have not done it already, you can still pick your scientist. You can take a look at the scientist biographies. There's up to 6 students per scientist. At this point, it's first come, first served. I've tried to do my best to match you with your preferred scientist. And if you would like to tell me that at the end you do not want to meet with any scientist, or you'd like to meet with more scientists, please email me at my email address right here. Lunch activity, as I said, this is optional. We can give you the space to meet amongst each other. Feel free to eat your lunch while doing so. It's lunchtime after all. And we provided you with another way to communicate amongst yourself with a Slack link here. It's pretty easy to sign up. Click on the link, enter your email address, and you'll be up and running. The office hour session. This is your time to collaborate, to have with CSM expert users. On a given day, we'll follow the practicals that are online for that same day. It doesn't mean that we cannot answer a question for outside of those typical practicals, but we're going to focus on what's there. On Friday, you're going to have the possibility to work on several exercises that correspond to different working groups. Ocean and sea ice, land, biogeochemistry, atmosphere, or Chem, and WACM. And there's going to be experts in from every single of these working groups present that day. Typically, the exercises are located at the end of the practical presentation. So scroll down to find the exercises, and they correspond to the lectures that were of the slide that were before. Please mute yourself at the beginning of the session. Raise your hand if you need help. And the way it's going to work is that when you have a question, we're going to listen to your question, and we're going to try to assign you with a helper that knows most about your question. Then Elizabeth is going to send you to a breakout room on which you can have a one-on-one conversation with this helper. And it will be very practical for you at this point to share your screen, especially if you have an error while compiling a code or performing some CSM command line activities. Asking questions. So this might sound trivial, but every year during the in-person tutorial, we have people that do not dare asking questions because they think the question is quote unquote stupid. There are no such thing. We all come from different backgrounds. Me first, I always have stupid questions. My background is in mathematics, not in atmospheric science, for instance, or land modeling or anything else. So I always have stupid questions. So what that could happen is for you to leave this tutorial with your stupid question unanswered. Please use this time to have your question answers. If you didn't have time to ask your question, that's another problem. Please contact me, and I will do my best to provide you with a person that could answer that question. So typically, I would like to say some words about creating a welcoming environment for everyone. Typically, Caroline Brinkworth, who is a diversity, equity, and inclusion senior personnel, gives this presentation. She's on paid time off this week. So I'm going to do my best to say a few words about this. Diversity and inclusion is very important at NCAR and UCAR. We strive to create an environment of full inclusion. We recognize that there's enormous scientific and societal benefits of including and valuing different perspectives and ways of thinking, and understand that diversity and inclusion are a fundamental requirement in achieving our goal of innovative world-leading science and engineering. Inclusion of different ways of thinking requires recruitment, development, and retention of individuals with different perspectives, experiences, and values. And to do short here, our goal at NCAR and UCAR is to build a diverse and inclusive workplace environment. Whatever your identities, intersection of identities, you are welcome here at NCAR and UCAR. There are 3 rules that we're trying to obey by all the times. The first one is to be kind to your fellow attendees. The second one is to be kind to instructors. Be nice to them, and they'll be nice to you. And the third one is to be kind to yourself. We forget sometimes about this, but be as kind to others as you are with yourself, and vice versa. In one of my communication, we sent you a link about the code of conduct. This code of conduct, you can access it using this link. It is here again. And whether you're in person again or using this Zoom link, please obey by this code of conduct. If you have not done it yet, please read it. We do not allow unacceptable behavior here. It means harassment, intimidation, or discrimination of any form or any inappropriate behavior is not tolerated here. There could be some consequences if we see some of this happen. You can be prohibited in attending any future event hosted or sponsored by UCAR, including fieldwork, if you're collaborating with NCAR and UCAR. and we will notify any infraction to have to your home institution. So it applies to everyone, attendees, instructors, UCAR staff, to all venue in situation. People are here to learn, okay? Remember, this is a professional environment, and if you need help or to report inappropriate behavior, please contact me or Elizabeth. So let's try and have fun during this week in the web process that Zoom allows us to do so. And now for the next 5 minutes, I'm going to take any questions should you have any. And please raise your hand if you have any question, and Elizabeth will give you the floor. No questions? Martha?
Hi, can you hear me?
Yes.
Yes, I was wondering for the exercises, I know you're going to focus on the ones that are in the presentations, but could we try to do something else, like try to use a different concept and then ask you questions if we have problems?
Yes, absolutely.
Okay, thanks.
Hi, yes.
Can you tell us again how to raise our hand in the chat? I'm not sure.
Yes, so you should be able, in the chat, you should be able, when you open the chat, you should be able to, let's see.
It's actually in the participant list.
In the participant, sorry.
Oh, okay.
If you open up the participant list, and then there's a bar of tools.
Thank you so much. May I ask a second question?
Yes.
How can we do a side-by-side with the terminal window so that we can see you and also work at the same time during the office hours?
So while you work, your Zoom window should be up, but your terminal window is not going to be in your Zoom window. Is this what you mean?
Yeah.
So you like on your screen, just have them on separate location, and then if you need to share your screen with a helper, just share your screen, and the helper will see what you see.
Thank you.
I think, Gunther, she was asked, I don't know whether I understood your question. If you want, you can reduce the size of the Zoom window from the full screen. If you hit the escape button, it'll reduce it to a small size, and that'll open up the remaining of your screen so that you can work on the exercise as well.
Thanks very much.
Oh, is this okay? Thanks, Gordon. I didn't misunderstand. No other questions?
I was going to add too that when we're doing presentations, if you'd like to change your view, up in the right-hand corner, there's speaker view or gallery view. So during speaker view, you can see the presentation and the speaker if they have their camera on. And then when we're having group conversations like this, you can have it in gallery view, where it kind of looks like the Brady Bunch with all the squares.
All right, if there are no more questions, so we're a little bit ahead of schedule here. Our next session starts in 5 minutes. If you want to take this 5 minutes to refill your coffee mug or tea mug, whatever you drink at this time of the day, please do so, and we'll reconvene in 5 minutes. Hi, Gökhan. Can you hear me if you're here?
Yes.
Yes, I can hear you.
Can you start sharing your screen?
Sure. Do you see it?
Have you reset your password? Hey, Elizabeth, there is a question in the chat, or Ryan, I don't know, from Hawkins, Linia, and Rose to everyone. Could you try to address it?
Yes, I will.
Thank you.
Yeah, I was about to respond in the chat for him.
Okay, thanks. So let's go ahead with our first session of this tutorial, which is an introduction to the community Earth system model, and will be presented by Gökhan Danabashoglu. Gökhan is a current CESM chief scientist, a senior scientist in the oceanography section, and a past co-chair of the CESM Ocean Model Working Group. The general subjects in his research are understanding the role of the oceans in the Earth's climate system and computational modeling of the ocean as geophysical fluid. And he will be giving this session. Thank you, Gökhan, for doing this.
Thank you, Gunter. So I'll go ahead and start. Well, I would like to welcome everybody first to the CESM tutorial, and it's a virtual one, as Gunter indicated. And it's unfortunate because this tutorial is particularly very useful to early career scientists, both to learn about CESM and also to sort of establish connections, both with each other and also with the NCAR scientists or CESM scientists in general. So unfortunate that we are having this in a virtual environment, and we are hoping that everybody will essentially come to an in-person meeting, hopefully next year, related to CESM, perhaps an annual workshop or a working group meeting, or maybe next year's tutorial participation. So in any case, I would like to essentially provide you some very high-level introduction to the Community Earth System model, also known as CESM. So what I would like to do, as Gunter indicated, everybody's background is quite different in this tutorial. So I would like to essentially provide a brief introduction to global Earth system models and what CESM is within that context. Then I would like to briefly mention a few of our efforts on coupled model intercomparison project, phase 6, that's CMEP 6, and I'm pretty sure that you all heard about CMEP and what it's all about. And I would like to then provide some updates on our ongoing activities. And the later part of the talk, the last part of the talk, will be more on the future-looking side. What are we doing with respect to our next model version towards CESM3? And I would like to mention many things here, at least introduce them to you, even if you are not necessarily interested in right now. At least it'll be in your mind, you'll remember that certain things existed in CESM or exist in CESM, so that in case you need them in the future, you can essentially come back to CESM and try to figure out what those things were. So I'll try to provide brief introductions on those aspects as well. So starting with global Earth system models and how CESM fits in to this global Earth system model in context, I'll try to cover that thing briefly. As you know, global Earth system models represent a virtual laboratory for experimentation. We cannot do real experiments with the climate, and we have only one, essentially, sort of member of the real climate. So global Earth system models provide a laboratory framework or numerical laboratory framework to improve our scientific understanding of observed events or climate change, and this can be historical or paleoclimate. We can use the models to simulate future climate change and its impacts. Another example is essentially we can use them to make predictions of weather, and more on the side of right now that's an actually emerging science area on climate, or perhaps more correctly, Earth system variability and predictability or prediction. And this the time frame for that effort covers from subseasonal to all the way to decadal time scales. And these are essentially mostly referring to initialized Earth system predictions. So global Earth system models use physical equations. And in terms of, with respect to the ocean and the atmosphere, for example, they would be Navier-Stokes equations from fluid dynamics. They use those equations to simulate key fields and processes in the atmosphere, ocean, land, sea ice, and land ice. These equations, of course, these are continuous equations, but they are discretized on a model grid. And an example is shown here. This is a regular lat-long grid. I'm not going to go into problems associated with such regular lat-long grids, but all these equations are discretized, and you end up essentially solving these equations at particular grid points, and they can be staggered or non-staggered. There are various methods to do that. Simply because it's impossible to solve these equations at really small spatial scales, it is just too costly. We end up discretizing these equations on grids, usually order 1 degree in the horizontal. So that's corresponding to order 100 kilometer resolution. That's for most of the modeling centers, 100 kilometers is sort of the workhorse model resolution. And clearly, there are many processes that are shown here in this schematic that are essentially occurring below that grid resolution, but they are important for climate, so that we need to include their impacts in the model simulations. And the way to do that, what we call them essentially parametrizations. These processes that are listed here, most of them are essentially represented in terms of resolved physics, and their impacts are incorporated into the model equations as parametrizations. For example, we don't use molecular diffusivity or viscosity. Instead, we use mesoscale, for example, in the ocean, and sub-mesoscale essentially mixing effects through parametrizations. And they are usually parameterized as diffusive processes in the models. So CESM is one such model. It's one such global Earth system model. And I included a schematic here to show the components of the coupled system. We have the atmosphere, it has chemistry, and it has a high top and low top version. We have the sea ice model, we have a land ice model, we have an ocean model, and it includes marine biogeochemistry. We have a model for incorporating the impacts of surface waves. River runoff model exists. And finally, we have the land model. And land model also has a biogeochemistry component. These individual model components exchange both states and fluxes through a coupler. So they communicate through each other. For example, land model waves its sort of wave information to the ocean model, and ocean model uses that wave information, for example, to parameterize or to incorporate the impacts of Langmuir mixing. And external forcing, such as greenhouse gases, anthropogenic aerosols, volcanic eruptions, and solar variability, are essentially incorporated through the atmospheric model component usually. We have in the ocean model, we can also account for geothermal heating, but in our regular applications, we do not use that feature. When you're essentially trying to use a coupled model, whether it's a regional version of the model or a global version of the model, depending upon your resources and depending upon what problem that you would like to solve, you need to essentially consider what I call sort of 3 different items and to assess your resources and your capabilities. The upper charts here refer to evolving model complexity. Coupled sort of modeling initially started as just atmosphere-ocean 2-component system, and that's sort of in mid-1960s to late 1960s. And you can see that over the years, they evolved a lot. They included many additional components, such as the sea ice component, ice sheet recently, and marine ecosystems. They're all included. So there is an increased complexity in terms of additional model components. But if you look at the upper right panel here, not only additional component models came on board, but each component model also increased in their complexity. So hopefully you won't hear, I'm at home in the basement and they're cutting our yard or grass out there. So there will be some noise coming from that. So each individual component, this is actually showing as a function of time, the model complexity. And for example, if you look at the atmosphere, there were very few features in the atmospheric model in early days. And as you can see by the thickness of these sort of shades, they increased in their complexity as well. So this essentially increases the cost and puts more pressure on your resources. Another thing that you need to consider, depending upon what problem, what science question that you would like to answer, is to consider how many ensemble members you would like to essentially perform to essentially entertain or to determine your signal to noise ratio. And I'll show you one example of that thing later in the talk. You can start with, this is sort of, I mean, in the weather scale, it's going to be so-called butterfly effect. When you start from your initial conditions, a slight perturbation of the system can lead to different sort of states further in time. And depending upon whether you want to essentially assess, for example, precipitation likelihood in a certain region, you may need to essentially perform multiple ensemble members of the same model. And another constraint that, or another thing that you need to consider, what resolution you would like to use in your study. And this is essentially showing 4 different atmospheric model resolutions. T stands for triangular spectral truncation. T85 is roughly 1.4 degrees. T42 is about 2.8 degrees. And as you go to T30, 340, these are essentially less than order a few tens of kilometers in the atmosphere. So if you're interested in essentially higher resolution in a certain region or in the globe, essentially, you need to consider finer resolution. Of course, it comes at the expense of more computer time. And that's why this chart is given here, or this schematic here. You need to allocate your resources based on what science question that you want to answer, considering how complex you want the model to be, how many ensemble members you would like to have, and what resolution you would like to have. And some modeling enterprises also, you can do regional grid refinement. And in our atmospheric model with the SE, spectral element dynamical core, regional grid refinement is also possible. And you'll hear more about these during this week. Another, so just back to CESM, this is just to give you an idea about the organizational structure of CESM. CESM consists of 12 working groups, and our newest working group is the Earth System Prediction Working Group. All the ideas essentially come at the working group level. If you would like to essentially have engaged with CESM community, and if you have ideas about sort of community projects, community integrations, you can attend these working group meetings. Usually there's one working group meeting for each working group during the summer workshops, and then the working groups also meet during the winter time or springtime each year. And then there's a scientific steering committee about the working groups, and then we have also an advisory board at the top, essentially. But the real essential ideas come from below at the working group level. And I just wanted to also mention that the CESM project has been in existence roughly for 25 years. So it's a lot of experience altogether. So CESM code base can support a range of climate science goals through a single model code base. It can be used in single column applications or coarse resolution applications. And for example, if you use it as a single column application, for example, in the ocean model or in the atmosphere, it can be used for example, vertical mixing parameterizations, and they can run on really laptops. We have coarser resolution versions of the model, and they can be used for long simulations or several thousand-year simulations, and they can be primarily used for example, paleoclimate applications. And the same code base can be used in higher resolution simulations. So as I said, in our CMEP applications, we tend to use order 1 degree horizontal grid, but we have model versions, and I'm going to show you an example later on that can be used also like 1/10 of a degree ocean model resolution coupled to 1/4 degree atmospheric model resolution. The code base itself can support many possible simulations. All components in our default configuration can be active, so all components can be active. But all component models also can be replaced with data, so-called data models. An example of this thing, for example, is an ocean-only or ocean sea ice coupled simulations forced with atmospheric reanalysis products. In that case, the atmospheric model is simply a data model, reads in the data sets that are needed to force an ocean model or ocean sea ice coupled model. So that configuration is available. We have other simpler model configurations. For example, Aquaplanet. We have several dynamical cores in the atmospheric model, and I'll show you examples of that. And you can run a slab ocean model for some applications. And there are many and numerous options are available within each component. And we are also supporting an increasing number of component sets and configurations as out-of-the-box available configurations. And I'll talk about a little bit more about more recent efforts on simple models within the CESM framework. So coupled model intercomparison efforts, that's CMEP 6. So just to make sure that everybody is aware of this effort, as you know, including CESM, many modeling groups, over I think right now 40 modeling groups are participating in this effort, CMEP 6 effort. What it is actually quite time consuming. It requires both computational resources and people resources also. It essentially involves at the core so-called DEC simulation, that stands for Diagnostic Evaluation Characterization of Clima. It requires essentially each modeling group, participating modeling group, it's like an entry card. You need to run order 500 years at least a pre-industrial control simulation, 1% CO2 increase experiment, instantaneous quadrupling of the carbon dioxide concentration, and CMEP. These are atmosphere-only simulations. In addition to that, CMEP is essentially designed to address certain scientific questions, and it has certain themes. And these themes are given here: systematic model biases, and you can try to address those. There are certain studies looking into variability, predictability, predictions, and future scenarios. And you can also look at response to, for example, external forcing. And around those themes, there are so-called endorsed model intercomparison projects. And there are many of them. And CESM actually participated. Some of you may be familiar with these model intercomparison projects. CESM participated in about 20 plus intercomparison projects. And we provided essentially 2 sets of model simulations for CMEP 6. The first, more extensive set uses our nominal 1 degree horizontal model resolution. And we participated both with low top with limited chemistry. That's the Chem 6 model version, community atmosphere model version 6. And then we also participated with higher top with more extensive chemistry model version for the atmospheric component. That's the WACCM, whole atmospheric community climate model. For, as I said, for cheaper applications, for maybe paleo studies that can be used for paleo applications, we also participated and created and participated a 2-degree atmospheric model version. All the other components are using the same, there's like the ocean and the sea ice models are still using 1-degree atmospheric model, sorry, 1-degree horizontal resolution, but the atmospheric model is at 2-degree resolution here. And these are all available to the community. And if you're interested in learning more about these solutions, we have actually an AGU CESM2 virtual special issue. We are expecting total 70 manuscripts for this purpose. 40 of them are already published or submitted, and you can essentially go to this website and then find all of these manuscripts. The ones that are published, they have a DOI number. The ones that are still in review, they're also available, and you can get their PDF copies here. And the primary overview manuscript is the Community Earth System Model version 2. I was the lead author for that, and that has been available from the website as well. So I don't want to spend too much time on this, but in case you hear about this, and you probably heard about this thing, most of the new, well, I shouldn't say most, quite a few of the newer model versions, not just CESM, but other models, couple models from other modeling groups as well, they are essentially producing a larger equilibrium climate sensitivity than their previous versions. And for those of you who are not familiar with what equilibrium climate sensitivity is, it simply represents equilibrium change in surface temperature when CO2 is doubled. So you take the pre-industrial control simulation, it has a certain level of CO2, you double it, you run it to equilibrium, and then when you, at equilibrium, you look at your surface temperature, you difference it from the beginning state or the pre-industrial level, and that gives you the equilibrium climate sensitivity. In practice, of course, it's not possible to run it for thousands of years, these models. They take too many resources. So you try to come up with an estimate. And I just, this is a chart from a paper by Jerry Neal et al. It shows equilibrium climate sensitivity as a function of transient climate response. Transient climate response is a lot easier to obtain, and perhaps it's more relevant for society. It simply represents, you run 1% CO2 increase experiments, and you look at your surface temperature at the time of CO2 doubling and difference it from the original state, and that is the transient climate response. The bottom line here is that in all the older versions of the models, equilibrium climate sensitivity was not really larger than 4.5 degrees. And in the new model versions, they are now in excess of 4.5, in fact, over 5 degrees in quite a few of the models. And sort of I circled the CESM solutions here. And there's no single sort of silver bullet why this increase happened. What we found is essentially in our studies, small changes to cloud microphysics and boundary layer parameters can essentially lead to these increases in equilibrium climate sensitivity. And what happens over the southern ocean latitudes appear to be quite important regarding cloud feedbacks. So I'm sure that you either heard about this thing or you'll hear more about it. Another plot that I wanted to show you is a model performance summary. This is coming from our climate model analysis toolkit developed by Jan Fasula, and this is available. And what it shows here is that in the horizontal axis here, it shows a bunch of models participating in CMEP 6. And in the vertical axis here, it shows about 20 or so atmospheric or surface fields. And they are essentially compared to available observations or reanalysis products in terms of their mean, in terms of their annual cycle or seasonal variability rather, and sort of intra-annual time scales as well are included. And energy, water, and dynamical variables are included here, and they are color-coded. For example, orange variables represent energy-related fields, long-wave net, short-wave net at the surface. So in this, and there's some kind of, based on this comparison, how good the comparison is, there's a score assigned to it. You want to be on the red side here. Blue numbers or green numbers, especially blue numbers, are not so good. So I just wanted to essentially highlight that in the top 10, roughly, I believe, our 4 CESM contributions are highly rated, meaning that the CESM model simulations are among the top couple model simulations in representing observations based on observational-based analysis or results or reanalysis products. So it's quite good for CESM, and this is available also in a paper by John Fosulo. Okay, so what's going on? And I just want to provide some brief updates now. We have essentially the main CESM 2.0 version of the model was released in summer of 2018. And since then, we have had 3 what we call incremental releases. These are not answer-changing releases. They're essentially adding more out-of-the-box configurations available to the community. And we're anticipating that there's going to be another release in September next month. And this is going to be an answer-changing release. It's going to include some additional features on top of what we had released earlier. And there are some changes in the land model or new functionalities, for example. And then the ocean model is going to also include a version of its new ocean component, modular ocean model version 6, that's MOM 6. And I'll mention a slide, show a slide on that at the end. Another, as I indicated, we have newly formed a new working group, Earth System Prediction Working Group. And the idea here is essentially this working group will serve the CESM and broader geoscience community by facilitating and coordinating fundamental research focused on understanding and advancing research on initialized Earth system predictions on timescales from subseasonal to multi-decadal. And we will perform large ensembles of initialized predictions that cannot be afforded by the individual PI. And they, just like our CESM1 large ensemble or CESM1 decadal prediction large ensemble, they'll be available to the community. And we have been actually doing quite well in terms of our predictions. This is showing essentially 2-meter air temperature skill. Skill is shown here, so larger number is good, and from several modeling groups. CESM results are shown in blue here, and we are doing much better than some of the other center skill reported by some of the other centers' prediction systems. On the decadal time scales, we have a 40-member large ensemble, and this is essentially being used a lot by the broader community, both at the national level and international level. And I wanted to show you just one quick example here. This is showing skill in summer precipitation over the Sahel region here, in this box region, over 3 to 7 year, let's say roughly 5-year lead times. The top panel here is the anomaly correlation coefficient, is shown as a function of ensemble size. The blue line here is uninitialized predictions or uninitialized simulations. They are not predictions, and it's just uninitialized runs. We don't expect any skill necessarily. And the decadal prediction large ensemble, the red line here, is from our initialized system. So for this metric, it's easy to beat the uninitialized system, so there is no issue there. But another important metric for prediction simulations is so-called persistence. Is the next year going to be the same as this year? And you can see the persistent line here at the dash line, shown as the dash line here. In order to be able to predict, beat persistence, you need over 30 ensemble members. In order to be able to beat persistence at the 95% confidence level, you need 30 ensemble members. So this is essentially showing an example of why you need multiple ensemble members. And of course, this depends upon geographical region and the field that you are looking for. And this is showing a comparison of our decadal prediction system. Blue is uninitialized, black is the OBS in this case, and then the red is our decadal prediction system. So it's doing quite well in terms of essentially predicting the sort of low frequency signals in precipitation in this region. Okay, I mentioned earlier that you may need multiple ensemble members, and this is just to show you an example of that. As I mentioned earlier, we have CESM1 large ensemble simulations available for community's use. And I wanted to show you what I meant by that. So what is shown here is the sea surface temperature variability with a focus in the North Atlantic. It's usually referred to as Atlantic multidecadal variability, but you don't need to know that. The top 4 lines here, or 4 panels here from left towards right, are observational or reanalysis-based estimates of sea surface temperature anomaly, its low frequency component. And what is shown in the remaining 20 panels is just by changing the atmospheric temperature field in the 16th digit in its initial conditions, you can get different representation of this variability as shown here. So if you're interested in what's happening, for example, in the South Atlantic, this is showing, for example, cold anomalies. This is showing warm anomalies. So you need to be able to run multiple ensemble members to get some confidence on which one is essentially more likely. So that's why you may need to use it, multiple ensemble members. But I wanted to highlight that this kind of product is available for everybody to use for the community. Indeed, we're essentially performing a new large ensemble, CESM2 large ensemble. It's in collaboration with our colleagues in South Korea. The previous large ensemble was performed only with 40 ensemble members. This new one is being performed rather we will be producing 100 ensemble members. This is slightly older slide. Actually, right now, about half of it, half of the ensemble members have been completed. We are anticipating that the full data set will be completed by December 2020. And after Seymorizing, making sure that the outputs are standard and all that, all of the data sets from CESM2 large ensemble will also be available to the community, likely in early 2021. I'm sure that you'll be using this data set a lot. And just coming back also, we have also data assimilation capabilities within the CESM framework. And we use data assimilation research testbed for that purpose. At our current research level, we have a prototype of what we call strongly coupled data assimilation system, meaning that the atmosphere and ocean model use a single covariance matrix rather than 2 independent ones. So a prototype of this data assimilation system within the fully coupled framework is running. But I wanted to make sure you understand the difference here. There are various ways of performing data assimilation. This is using Ensemble Kalman filter, meaning that each component model requires multiple members, up to maybe 40 or even more members running simultaneously to get the ensemble spread correct or reasonable. And that you can imagine, if you are using 40 ensemble members, that means it's going to cost you 40 times more than a regular coupled system to run this. So it is not really economical. So in order to be able to essentially provide a more affordable data assimilation system, we have recently developed a new approach. The approach itself is not new, but its implementation in Dart is new, so-called ensemble optimal interpolation technique. I don't want to go into many details here, but in contrast to the Ensemble Kalman filter approach, which required running multiple ensemble members, this technique is essentially requires running only one ensemble member, but the spread is essentially based on some previous knowledge of possible spread that comes from an existing simulation. And this is rather affordable even at high resolution frameworks. And another thing that I wanted to mention, we do also have a high resolution version of the model, and the results from this are already available. This is actually a collaboration under the IHASP umbrella, International Laboratory for High Resolution Earth System Predictions. It is between us, Texas A&M University, and also the Qingdao National Laboratory for Marine Science and Technology. We are using a slightly older version of the model for this purpose, CESM 1.3. The code base has been substantially rewritten to run on the machines in China. They are Sunway systems. They are somewhere in between CPU and GPU-based systems, and that code base is available, and then the manuscript has been recently accepted, I believe. I think it's accepted in GMD, Geoscientific Model Development. And if you are interested in using these data sets, what we have is a 500-year pre-industrial control simulation. We have a 1850-2100 transient simulation run with RCP 8.5 scenario. We have an 80-year 1% CO2 increase run. And we have also 4 cycles of ocean sea ice coupled forced hindcast simulations for the 1958-2018 period. As of June 8, we made some of these simulations already available. I should also mention that we have also completed contributions for HiResMEP, 130-year 1950 control, 1950-2050 transient simulation, and 1950-2050 just atmosphere only simulation, and its corresponding low resolution simulations are also available. So some of the simulations were made available, solutions available on June 8. The rest of the data sets will be available by the end of this year. And there's a manuscript already just submitted, actually. You can find that manuscript from the IHASP website. If you type IHASP on Google, you'll get to that web page. Okay, towards CESM3, so this is the last part of the talk. And I just wanted to give you an idea about where we are going in our model. So we are essentially developing idealized modeling toolkits. This is going to make it a lot easier to essentially know what idealized model configurations available within CESM. We'll be also developing some new idealized model configurations, such as extensions of the single column ocean model, what I call pencil model, that'll be hopefully including the Ekman component as well. But it is going to be essentially a nice framework to figure out what's going on with CESM simple modeling efforts. We are recently essentially looking into increasing our standard atmospheric model resolution higher than what it is already. And also not only increasing the vertical resolution, but also we would like to increase the model top. And this will essentially, it will not be as high as what our high top model does, but it will be extending higher than the present low top version to improve vertical resolution in the free troposphere and stratosphere. And the idea is particularly to get a better representation of the QBO, that's the quasi-biennial oscillation. And it's shown here from ERA reanalysis product. And you can see as a function of vertical resolution how this oscillation is represented in the model. So we are right now shooting for around 500 to 600 meters resolution within the free troposphere. Another thing that we are actually looking into is changing our atmospheric dynamical core from the present regular lat-long finite volume dynamical core. And we are considering 3 options. One is the SEDI core, that stands for Spectral Element Dynamical Core. It's a highly scalable hydrostatic dynamical core, and you can essentially do grid refinement with that. And it can run also physics on a separate, usually coarser grid for uniform grid applications as well. We have also so-called finite volume 3, FE3 dynamical core. That's again in the cube sphere version of the regular lat-long finite volume dynamical core. And the third dynamical core is MPAS. That is an irregular grid dynamical core, and it's shown here in a sort of hexagonal grid configuration here in the lower panel. So we'll be having some sort of a backup in these dynamical cores either later this year or likely early next year. And as I alluded to earlier, we are also changing our ocean model from POP2 which is used in CESM2, it'll be MOM6 in CESM3. We have a development prototype, MOM6 version, running within CESM framework in both fully coupled and ocean sea ice coupled configurations. Currently, we are using a 2/3 degree horizontal grid. It's a tripole grid with equatorial refinement with 65 vertical levels. And as we speak, we are conducting extensive simulations to gain more experience with this code base, because it's using a different vertical grid structure or vertical discretization approach. So it is, we are trying to learn how this model behaves essentially. Lots of documentation and training opportunities are possible. We are conducting webinars to sort of make sure that people know about this thing. And there are certain practical cases, use cases available on the website as well. And if you have more questions about this thing, Gustavo is one of the organizers of this tutorial. I'm sure he'll be happy to answer any MOM6 related questions. And just for your information also, when I said we are going to release CESM 2.2 in September, likely September timeframe, there's going to be an early friendly user version of MOM6, functional release version of MOM6 available in that model release as well. And this is just to show you that model is working, and then we are getting reasonable solutions, for example, in representation of Atlantic meridional overturning circulation at 26 degrees north compared to other model versions, just showing the time series here. Okay, with that, 40 minutes exactly, and I would like to stop, and I just wanted to show you the similar picture as what Günther showed. If it weren't for the virus, we would be actually in this building up here conducting this tutorial in the main seminar room. In any case, thank you for your attention, and if you have any questions, I'll be happy to take them now. Thank you.
Thank you so much, Gökhan, for this great presentation. And so, yeah, let's open the floor to questions, and please don't be shy. Raise your hands and we'll give you the floor. And, you know, for you to take the time to think of a question, I would ask the first question, simple question, hopefully. Are the previous version of CSM now becoming obsolete?
Well, not quite, because we are still supporting. In fact, we changed our recent data policy to support some of the earlier code versions, going all the way back to CCSM4, roughly 10 years ago. And there are several reasons for that. As university users, like graduate students and all that stuff, work with their older versions of the model, we would like to keep that support going so that PhD students can actually finish their thesis. And we're also made aware that some of the older versions are still used heavily by the university community. And so that's one reason. The second reason is that CESM1, for example, decadal predictions and the large ensembles are still using CESM 1.1 code base. And that's roughly 10 years old. And that they are also being still supported. And similarly, our high-res simulation CESM 1.3, almost 8 years or 9 years old, and we are still supporting that because that's the only high-res version that we have right now. So they are, I guess the short answer is, yes, we are supporting the older versions within reason, though.
All right, so we have a couple of questions. Marta, go ahead, unmute yourself and ask your question.
Hi. Yeah, so, well, that's a question I asked you, Günther, on my email, because I'm curious about how you do coupling. And one thing, the question I have is that if you're using different initial conditions, for instance, an ocean reanalysis and atmospheric reanalysis, how do you make sure that these initial conditions are consistent? Do you like use a protocol? Do you check that before?
Unfortunately, we don't have anything automated at this point. And you need to be really careful as a user how to do that. For example, from the ocean side, if the DA product, reanalysis product, is performed using our ocean model, then there is no issue because then it's done in a consistent way. However, we have also, in fact, I've done that in the past as well. If you would like to take, for example, GFDL's data assimilation system and bring the ocean initial state to our version of the model, you need to make sure that the bottom topographies, for example, match. You need to make sure that the temperature and salinity are properly filled in case there's a new sort of ocean regions due to changes in bottom topography. But more importantly, you need to obey, for example, in the ocean model, barotropic baroclinic split. You need to make sure that the vertical integral of baroclinic mode is essentially 0, and the vertically integrated total velocity adds up to the barotropic mode. And you have to, unfortunately, do those things offline and make sure that everything is consistent. I mean, you can imagine that every system is different, so there is no easy way to do that. Does that answer the question?
Yeah, but well, it answers partly. You also have the question if you are using, for instance, if you have different, you get the data for the atmospheric part from a reanalysis, but then the data for the ocean part from another reanalysis, and you also need to do some checks to make sure that they both match.
Yes, I mean, that's a big issue. I mean, right now we are dealing with something similar to, regardless of what you do in that case, since the two reanalysis products are not the same. And that's why I showed that slide on coupled data assimilation. That's one of the ways that you can avoid inconsistency between the two systems. And I think whatever you do, there's going to be some kind of initialization shock of the system that you need to essentially be careful in the interpretation of early part of the results. And it'll likely end up you'll end up likely using bias correction for that purpose.
Okay, Maribeth?
Hi, thank you for the presentation. I was wondering, in the MOM 6, you were talking about how there's the 3 different grids that you could use, and I was wondering what would be the benefit of using the I believe it was a hexagonal grid versus a rectangular grid.
So that was actually not MOM, that was the atmospheric dynamical core options, essentially. Okay. But so that is MPAS that is the MPAS. It's on irregular grid. One advantage essentially of that configuration is you can do regional grid refinement in any way, any region that you would like to have. So that's one advantage. But it's not necessarily the grid structure per se. It's essentially of that system. It's in irregular grid, and it allows you to do that. I guess it comes with the grid. So that's one big advantage. You can do regional grid refinement without going into, you can do it in multiple regions in a single global application. So that's one beauty of it. But it's very expensive because it's irregular. You don't know where your nearest neighbor is, and it computationally becomes extremely expensive. And also, potentially, it can represent the coastal regions, for example, much better. You can essentially, for example, you can do grid refinement in, let's say, in Gibraltar region. You can put a lot of grid there with higher grid resolution, and then make it coarser, so it will essentially adjust the coastal regions or adapt the coastal regions a lot better. So those are sort of 2 or 3 advantages. Probably I missed a few, but it's expensive though, very expensive.
Okay. Any other questions? We have time for one more. Kin?
Hi.
I'm sorry if I mispronounce your name. Please correct me if I mispronounce your name.
It's correct. Yeah, can you hear me?
Yes, go ahead.
Yes. Yeah, thanks for the lecture. And you mentioned the refinement. When we need a higher resolution, we can do refinement for a certain region. And meanwhile, we can also use regional climate model. So I wonder what's the difference between the two approaches and what's the pros and cons of them?
Well, the biggest part that I can think of right now is essentially when you do regional refinement in a global modeling context, you allow two-way grid interaction. So in other words, what's happening in the regional in the refined area can directly communicate without any sort of ad hoc issues, and everything is done in a conservative way in a sense because it's within the same system. When you do it in a regional coupled model, in fact, we do have a regional coupled model version of it. It's essentially supported by Texas A&M as part of our collaboration. The issue is there is essentially, it is not embedded. If it is not embedded, then you have to provide some kind of boundary conditions. Then you have to deal with sort of sponge layers and all that stuff. And you are likely at the mercy of the boundary conditions that you are specifying at that point. Even if it is embedded, your regional system is embedded in the fully coupled system, which we have a version as well that you can use, then it becomes essentially one-way coupling technically. Some people call it two-way coupling because of the SST interaction with the atmosphere in that finer grid. But that's, in my view, the biggest thing. However, a big disadvantage of regional refinement in a global coupled system is that if you do, for example, North Atlantic refinement, you end up essentially spending pretty much your computer time in that region in any case. Your CFL condition will likely be dictated by the time step or grid resolution in that region. So you are going to be paying a lot of computer resources. My understanding is that if you do some sort of regional refinement with MPAS, 90% of the resources are being spent in that regionally refined region. So you need to be careful with what your science question is.
Thanks.
There's another question from Rachel.
Oh, thank you. Would you mind talking a little bit about the ICESM and what version is supported on?
Which one? ICESM? That's the isotope-enabled version? Is that what you're talking about? Yeah, that is so you can essentially talk to Betty and Esther about that thing, and you'll get more accurate information probably from them. It is unfortunately right now that it is supported only in older version of the model. I think it's supported in CESM1 or CESM4. I'm not 100% sure. We had a few meetings to bring all of the features of the isotope-enabled version to a more recent model version. Unfortunately, there is some work going on, but it won't be completed probably for another year or so because it was more extensive than we originally thought. So I think, if I'm not mistaken, it's CESM4 or CESM1 based at this point. And that's another reason that we need to essentially provide support for that version. But please ask Betty or Esther about that.
Thank you.
You're welcome.
All right. Thank you, everyone, for your questions. We reached the our time for this session. Thank you so much, Gökhan, for doing this.
You're welcome.
Have an 10 to 10 minutes break. Let's reconvene at 10, and we will move on with the atmospheric Q&A panel session. So see you in a few minutes. Okay, so let's go ahead and start with our first Q&A panel, which will be moderated by Cécile Annay. And I'm just going to say a few words about her and then just give her the floor as she will organize this. Cécile Annay is a scientist in the atmospheric modeling and predictability section, and she's deeply involved in the development of the community atmosphere model. As a liaison of the atmospheric model working group, she assists the climate modeling community in all aspects of using CESM and CAM. The subject that she's going to be moderating today is a question and answer about the atmospheric model. Thanks, Cécile, and the floor is yours.
Okay, thanks everyone. And I have 4 panelists for this session. I see 3 of them so far. And I was thinking I was going to share my slide with the question to share my screen. Then let me try to share it. Okay, then this is the 4 people who are going to help to answer your question today. Then there is Rich Neal, who is, we try to get people from every working group. Then Rich Neal is really involved in the development of the atmospheric model working group. He used to be the co-chair of this working group. Ayla is involved in the climate variability and change working group, and she's the co-chair, one of the co-chair of this working group. Simone Expertise is the chemistry climate. She's the liaison of this working group, and Mike is the WACAM liaison from the WACAM working group. And the way I was thinking to do this, it was, people post some question online, and we are going to go through these. I'm going to show the question here, sorry. But then we will, if you have other questions, I will ask that you raise your hand. Then on the Zoom call, you have an option to raise your hand, and that you raise your hand there, and we will also take your question. Okay, then the first question here was, and we have the 4 panelists, and please, you can ask, yeah, you can answer. Raise your hand. I have shared a question with you before, then raise your hand when you have a question you want to answer. Okay, and then the first question is on the screen right now. Then can CAM6 contain substantial modification of every atmospheric parameterization except for the radiative transfer? And which process are you targeting in CAM7? And maybe answer can come from the different working group too.
Yeah, this seems like a question for Rich, but is Rich here?
Yeah, Rich is there, yeah.
Sorry, I just came, what do? Do I just speak?
Yeah, you just speak.
Answer this question.
The question is on the screen.
So, yeah, you're right. Radiative transfer, we probably won't modify from the perspective of the scheme. I'm sure some of the optics, kind of constantly being updated. So I could be explicit about what we're doing within NCAR, within the atmospheric section, which is we're focusing on aspects of improving the existing CLUB scheme. So CLUB is a cloud layers unified by binormals. This is a high order turbulence scheme, but there are shortcomings in the way it handles momentum and the processes associated with that. So that will be a focus. It seems a small thing, but the impact is undoubtedly going to be big on simulations. The second thing is we're testing at least a unified kind of boundary layer parcel type. You could imagine convection, but a unified parcel boundary layer turbulent type scheme. It's called EDMF, eddy diffusivity mass flux. So the eddy diffusivity is the boundary layer component, and that is essentially the formulation merges into a mass flux type scheme in the free troposphere. So that's the kind of, that I would call that the moist turbulence focus. On the microphysics side, where it's currently a 2-moment scheme that considers distributions, number concentrations, sorry, of ice and liquid. And I think, I'm not too privy to that exactly, but I think the modification that's coming is considering Graupel, so an extra categorization of ice. And so that's pretty important, I believe, in intense storms. So as we go to high resolution, I think that'll be pretty important. I think that's, you know, even at this point, we're not like, we have a very distinct plan for the next 5 years. You know, there is always the capability, the possibility of considering new things along the way. So I'll stop there.
Okay,
yeah. Can I just add, I don't know if you mentioned this, the vertical resolution is going to change to be higher and to have a higher top. So somewhere in between CAM and WACM.
Yes, thank you. It's a good point, Ayla. Yeah.
And a increased resolution in the boundary layer too.
Okay. Okay, then the next question, it's more about how to run the model. Then we can find a variable available for output or add them in the source code of CAM. Is there anywhere where we can find just the list of variables that are available for output and the definition?
Yeah, it's kind of a catch-22 in that you have to run the model in order to see the list that is, because each version of the model has a different list of outputs that are available. And so when you run the model, you get a log from the atmosphere model. It starts with atm.log and then a number. And if you look in there and you search for the words master field list, all in caps, it's followed by a list of all of the outputs that you can do in the particular configuration of CAM that or WACM that you're running.
Yes, thank you, Mike. Yeah.
There's another way though. You can also look at your log file if you run for 5 days and you get the output.
It's what they said, yeah.
Oh, log file. I didn't hear that.
Yeah, and it's the only way that there is. They used to be, they will post for different version, but as Mike said, the model became too complicated with too many different options. Then you have to generate the master field list on the fly by running a 5-day or even a one-time step run.
I think you can still learn a lot though from what's on the internet, like from the older lists of the variables.
Yeah.
Maybe some things are out of date, but if you just Google CAM history fields, you get the CESM1 ones, which gives you some information.
Yeah. Okay, then what are the basic principles behind cloud microphysics in the atmosphere model and how they can be altered? Who wants to say something about this? Maybe Rich? Oh, you are.
Yeah, I can try it. It's not really my area, but so basically the microphysics schemes, the one that is in there, which is the second version of the Morrison-Gettleman. And so it considers essentially ice and liquid. And what tends to happen, well, the process that happens is that to form, so for condensation to form, the relative humidity has to be a certain magnitude, but also there has to be a presence of aerosols. So these can be cloud condensation nuclei, so just small particles. Dust is one, and black carbon, for example, sulfates. And so the water process that happens is, activation. So these particles are allowed to kind of condense water on their surfaces. This is true for liquid and true for ice. They can also form spontaneously, and that's called homogeneous nucleation, whereas the first process I described was heterogeneous. Anyway, the idea is that with this 2-moment scheme that's in there, so essentially there's a mean mass of liquid and ice once you get that nucleation, and then there's a number concentration. So it says how, it basically tells you how the distribution of the particles from small to large associated once all these particles nucleate. And essentially there's a lot of physics then that's involved in terms of at a certain mass or a certain size that they reach, then they fall out. So it's called order conversion. And then an additional process of that is the collection of cloud water as they fall. So the large particles fall, and they fall through cloud below them. Ice is a little bit different, but this is ostensibly liquid. And then essentially, that can fall through the ground and also start to re-evaporate near the surface when in clear air. So that's a very basic examination. And these are all process rate limited. So you could imagine that if you have, you can activate these cloud particles at a much lower relative humidity. It could be a tunable parameter, but also a number of these processes, such small scale, everything is parameterized from the smallest scale. And like I say, there are a number of rate constants, re-evaporation rates, et cetera, that can be modified.
Okay, thank you, Rich. Okay, then the next question, it's more a practical question, and I'm not sure I understand the question. How to run a couple simulation spin-up in the case of changing code from one component, it has CAM6. If somebody, I can answer something, or someone you want to.
Maybe it's about, the spin up. How do we actually, say, set up a model run, a B case, if we change the code? Meaning, suddenly you change the code, can you still apply it? And what we usually do is start with a pre-industrial control simulation to make sure that the model is balanced. So code changes may change the atmospheric imbalance, but we want to make sure before we start a B case that we actually have the model in balance before we start any transient simulations.
Yes, thank you, Simone. And I will add to this that you want also to start usually an hybrid run, and it's something you will see in the practical, to make sure that the ocean is already partly spin up and your spin up is faster.
Did you say hybrid run?
Yeah.
Okay.
Yeah. Sorry, I don't pronounce H then. Okay, the next question is, does CAM6 CESM2 include the effect of fire aerosol on climate? If yes, where is that, and how to open this module? Then Simone, I don't know if.
Well, the thing is that what we do for fires right now is we are emitting fire emissions that are prescribed. So those fire emissions will, of course, then impact the clouds and directly and indirectly change the climate. And that's basically only about emissions. You can change them and then you get a different effect. Maybe this question may be also about interactive fire modules. The land model can also calculate the area burned, meaning that you can directly produce fire emissions from the land. And that goes in the atmosphere. However, at this point, we don't have a configuration yet that we have released, and that is valid. So we're still working on that.
Okay, thank you, Simone.
Yes, I'll just add that if in CESM1, we do have some historical simulations, single forcing runs where you can look at only the effects of the biomass burning aerosols. So if you just wanted to diagnose their influence in runs that have already been run, that might be useful.
Okay. Okay, then question on specified dynamics. Then by nudging dynamics to observation, the model tried to reproduce atmospheric fields and compare with observation. What's the point to do so? We don't have observation to nudge to for future prediction. What's the relation and difference with data assimilation?
So maybe I can.
Ayla? Oh, okay.
I mean, in terms of nudging, what we do is only dynamics. So we're not nudging atmospheric fields like, CO from satellite or something like that. And the idea is you take the winds and the temperature, or depending on the kind of nudging, surface fluxes, in order to reproduce the same meteorology. And then if you want to look at changes in chemistry, you have a consistent way, you have actually the observed meteorology you can then compare to observation of chemistry, but we are not nudging the chemistry variables. Data assimilation really is something like you start with a free running model and then you assimilate temperature fields or other fields into the model that then will go closer, and the winds and everything will develop closer to the observed state. So it's a very different process. We're just nudging to the already analyzed winds from GEOS5 or MERA or other products.
Yeah, just to clarify what you said about CO, I think you were saying that we don't nudge things like CO and chemistry, that would be data assimilation. And as far as what the point is, it can be very useful, for example, in getting the model to reproduce the observed ozone hole, which can vary from year to year depending on the specific winds and temperatures in the stratosphere. Otherwise, you have a lot of variability just from the climate. And so by getting the observed winds and temperatures, we can check whether the chemistry is working correctly, and then we can change single things like volcanic eruptions or other factors and see how that affects the chemistry in the stratosphere. And we do actually have some forecasts that we use to nudge sometimes for about 2 weeks ahead of time, and we produce a chemical forecast that's published on the web 2 weeks in advance.
Yeah, just to add on that, yeah, we run the chemical forecast, the WebChem forecast, and in addition to just what Mike said, it's also for aircraft campaigns, for recent campaigns, looking at things like existing conditions, comparing to observations, and also looking at, for aircraft campaigns, being able to look at not only what the wind field looks like, but also what will be the chemistry looking like up to 10 days ahead.
Okay. Okay, thank you.
Also,
yeah, go ahead.
Yeah, you can also just use it to look at the influence of one region on somewhere else. So you could nudge, for example, the stratosphere either towards the observations or towards another model simulation and see what was the influence of those circulation anomalies in the stratosphere on the troposphere. Or you could nudge the tropics and see what's their influence on the extratropics. So you could nudge locally in different regions and see their impacts.
And you can nudge from other model runs to isolate the effects of chemistry and dynamics.
Mm-hmm. Okay, thank you. Thank you. Okay, the next question is about gravity wave. Then the lecture mentioned that gravity wave is too fast to resolve. And because it's energetically weak, you can slow or even ignore gravity wave without affecting the result much. Is there any case that gravity wave is important and now we can treat it? Rich, is it you who mentioned this in your lecture?
I don't recall, and yeah, I hope I get this mostly right. I don't think I mentioned this. It might be from Peter.
Okay,
anyway,
and I don't know if somebody wants.
Yeah. I can say something, and I don't know if Peter's on, but I can definitely say something. So the hydrostatic atmosphere supports gravity waves, and a good way to see this, actually, the flow is generally very well balanced, that they don't have a very large influence on the flow, pretty small amplitude, as you say. But a good way that you can see these is if you do kind of these initialized simulations. So if you take the model and run it like a forecast, essentially, and you give it a state. And these states can be quite out of balance with what the model kind of likes as a balanced flow. And what you do see is waves propagating away from mountains, orography, essentially, because that's the regions where the state of the observed state, although it's not perfect, of course, is out of balance with that, with which the model likes. So you do see these quite fantastic waves propagating away, but the purpose of these waves is to essentially balance the thermodynamic fields that then give you a balanced flow, and then you don't really see forcing that's strong enough that would force these types of waves in a typical climate simulation.
Okay, the gravity waves Sorry. Yeah, gravity waves though are important in the stratosphere, and when you have a high top model, you have to parameterize them. So you have flow hitting the topography, and you also have fronts, and they'll generate gravity waves that are parameterized, and the drag is deposited higher up to.
I guess I was distinguishing between vertical and horizontal. Yeah, you're right. I'm talking about horizontally propagating, like density flows splashed. Essentially. Kind of corollary as a stone in the water, essentially. But, sorry, Isla, but you're talking about.
I didn't see the lecture, so that maybe that is what that was applied to.
We're going to go to the next question, but I want to remind people that if you want to ask a question live, you are welcome to raise your hand on the Zoom call, and then I will take your question. And don't be shy. Then the next question, it's probably for Simon and Mike. Then how can you add different photochemical reactions that are not already in CAM-WACAM, and how do you change their rates?
Maybe. So Mike, go ahead.
When you create a case, you'll find in your case directory under case docs, there's a file called chem_mec.in, and that is the input file that was used to create the chemistry mechanism. And there's part of the practical sessions that's part of this tutorial where we talk about how to modify that file and then use it as what we call a user mech in file, so that you can specify in the env build.xml. There's a cam config options where you can specify your own modified chemical input file, which will then run through what we call the chemistry preprocessor and create new versions of the subroutines that handle chemistry. And so for gas phase reactions, that's pretty straightforward. There are three different ways of specifying those. One is temperature independent, one is Arrhenius, and then there's the three-body TRO reaction rate. For photochemistry, for photolysis rates, it's more complicated because those are specified by reaction cross sections. So you need to have cross sections at all the wavelength bins that are in the model, and then the model integrates those with after multiplying by the actinic flux to calculate photolysis rates. Simone, you want to add anything?
Okay. Thank you, Mike. Okay, then the next question, it's again more practical session question. We can find some supported atmospheric grid with mesh refinement in the grid resolution definitions page. If we want to use a different refinement for the atmospheric model grid, what would we have to do? Create a new grid hour. Maybe I can answer this, or if Ayla or Rich. Because I think
documentation is
CSM. Sorry.
Oh, carry on.
It's going to be part of the CSM 2.2 release, and I think that at this stage, if they want to, if they cannot wait for the release, they would have to contact Pat Callahan for help to do the new grid.
Yeah, maybe
you want to add something, or?
Yeah, I can add that we do have for chemistry, we have the Musica version 0, which is basically chem. For that, we designed a wiki page. And in that wiki page, we are compiling information how to design a new grid and how to then also produce the emissions and input data that you need to run with this new grid. So there will be all this information. There are in part available, and there will be available I can potentially maybe provide the link to that wiki page.
Yeah, and you can probably add this in the chat. If you want to put the link in the chat, people can see it.
Simone, are we releasing something with CSM 2.2, a comp set with one of these refined, like CONUS or something?
Yeah, so for chemistry, you get the CONUS, regional refined grids. There is a comp set that will run.
Cecile, do you
And
just
I know
want to?
for CAM, there will be something coming in CSM2 too.
Do you just want to explain what regional refinement is, just briefly, in case people are unaware?
Go ahead. Yeah.
Oh, do you want me to do it? Yeah. So yeah, I mean, it probably is obvious, but just so people are aware, the capability we have with a new dynamical core, called the spectral element dynamical core, now allows us to run a global simulation that is, it doesn't have to be like equal resolution everywhere. It can now have a focus region. An example is over the US, where we can run much higher resolution there, often by a factor of 8 or 16, compared to the rest of the globe. So this is a nice regional modeling capability that we've developed.
Okay, thank you, Rich. I'm going to reload. I don't know what happened with the question. I'm going to reload them because it seems that they changed where we were, then we went through this or this. Okay, then the next question. Are you planning to develop a simple model consisting of two simple models coupled? It's a single column couple ocean atmosphere to study the heat and moisture exchange between the ocean and the atmosphere. I don't know, Ayla, if you want to say something about this.
Yeah, there are lots of plans.
Maybe you can say something briefly about simple model, if you want.
Yeah, so we have quite a lot of simpler models available now. Mostly they've been on the atmosphere side. If you just Google CSM simpler models, you should hopefully come across the website and see the options that are available. But now we're starting to go into coupled simpler configurations. So there's one effort underway with Andrew Gettelman and John Truesdale, where I think they are doing what was asked here, coupling the single column atmosphere model to a single column ocean model. But more generally, there's plans to make toolkits for coupled idealized modeling so that you can couple any configurations that you want together as long as they can be. So, and then we'll have tools to kind of, if you want to make your own continental configurations or bathymetries within the ocean, to set up your own coupled idealized configuration. So that's definitely something that's underway. It will probably be a year or two before the tools are really available to use, but we're looking for people to test them as we go along. So if that's something you're interested in, definitely get in touch with me. It's Scott Backman is leading the project together with me, but I can forward things along to him if you send them to me.
Okay, thank you, Ayla. Okay, then we got this question already. Okay, then this is a new one. Has CSM ever be used for medium range and short range weather forecasting? It is simulating a specified observed phenomena like tropical cyclone using at least couple atmosphere ocean. What are the main challenge? I suppose one of them is that you need high resolution. Do I have a panelist who wants to answer this?
I don't know about the tropical cyclone part, but CSM has definitely been used for forecasts from subseasonal to decadal timescales at the regular resolution. So, and those are available. And I think Jaga Richter is running them with CSM2. Sorry, there's available with CSM1 at the moment. So it's definitely being used, but more for intraseasonal to decadal timescales, perhaps less so for the weather phenomena, but maybe Rich has something to say about that.
Yeah, I mean, that's my understanding too. I mean, I would say one of the in terms of running weeks to months, I don't think we've done full, higher resolution, fully coupled simulations. And the biggest challenge in that framework is how to initialize the model and what to do with the fact that it drifts. So if you initialize a fully coupled system as a forecast system, what will happen is over weeks and definitely months is the system will generate biases in the ocean, which look like the biases you get if you just run typical climate simulations. And there's a lot of I'm sure go into the details, but manipulation and like detrending that is done in that state of the ocean to get a better forecast, essentially. So that's where all the devil in the detail and the effort is right now, I think. And for tropical cyclones, of course, you need high resolution. And 25 kilometers we find is kind of the minimum you need to get decent looking ones.
Okay, thank you. Okay, we had this one. Okay, we had this one already. I don't know why the question got reordered.
I think, do they change as people upvote them?
Yeah, maybe.
Well, people's downloading these.
Yeah.
Maybe you have to go up again.
This one we had. I'm going to reload to make sure that I don't miss one. But and we will just go through Oops, I'm going to go.
Yeah.
I'm going for the most voted. Okay, this one we did. 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 So we just did now. By nudging to observation, we just did this. We just did this one too. We did this one too. Okay, then this is a new one. What's the status of Musica development and how can we get involved and try to learn the model?
Yeah, so the Musica development is starting. Basically what we have is a ChemChem regional refined grid as defined as Musica at this point. And I just posted the wiki page there. We are trying to work on a tutorial, and the best thing is first to wait to the next release. So you can actually use the release version. The tutorial that we have done so far was just an internal one, but we will have some tutorial coming up, and that will be either totally online with also office hours, or it may be also more in person, like lectures, but that hasn't been defined yet. So really this wiki page should be a first start, and then we'll post more after the release, I think.
Okay, thank you, Simon. And once again, if you have more questions, Simon post the wiki page of Musica in the chat group. I don't know if my screen is showing there. Do you see my screen there? Or? Yeah, Simon post if you go in the chat group. And if you want to ask questions, you can raise your hand or you can post in the chat group too. Okay, next question. What are the limits of the atmosphere radiative transfer module? It has 10 times CO2 or variable amounts of other chemicals. Somebody wants to take this?
I'll give it a little bit of a go. I mean, so radiative transfer is kind of a special breed of scientists that research radiative transfer. I know that we have used done simulations with at least 10 times CO2 with success. It's hard to know whether it really is successful, given that it's a very warm state that exists. In terms of the problems that arise, my understanding, experience in the past has shown that problems arise in the moist physics in a very warm environment. So that allows very high levels of water species, and so that can that has led to strange behavior, and the model can crash. But as to the exact limit of the kind of radiative phase space, if you like, of where it operates, I'm not sure. I'd have to look that up.
Mm-hmm. Okay, somebody wants to add something? Or?
Just the first thing that I've experience crashes when you start ramping up CO2 is the ocean, and you just have to reduce the ocean model time step having to do with the uptake of CO2 in the ocean, I believe.
Okay, thank you. Okay, next question. What's the major difference between a variable resolution model and a regional climate model? How does the variable resolution model simulate regional feature compared to a regional model or a coarse resolution model?
Well, I guess the main difference is the feedback between the high resolution region and the rest of the globe. In the regional model, you have to specify what the larger scales are doing at the outside. And so there's no interaction between the high resolution region and outside of that. Whereas in the variable resolution one, you can have two-way interactions between the higher resolution and the rest of the globe. Rich is probably a better place to answer the second part, but I think there are definitely features that are better with the, obviously, like tropical cyclones and things you can capture when you have variable resolution.
Yeah. I mean, in terms of the way the model performs, when you do this in a regional model, if you go from essentially low to high resolution, you do the stepping down. And so that in and of itself can kind of result in strange, boundary features and kind of, spurious things that look like they're right on the boundary. Whereas, doing the regional refinement in the global model, it tends to be much more kind of continuously stepping down between the low and high resolution. So that's one problem that it helps with. It doesn't get rid of it completely, but it does help.
Mm-hmm. Okay, thank you. Next question, how are surface emission of anthropogenic gas and aerosol usually treated? Are they treated at all, or does the model work in concentration directly?
Yeah, we have emissions in molecules per, for surface, I guess it's
per cubic centimeter
per second. The same as for 3D atmospheric emissions, but they are in separate groups in the name list.
Yeah, and different. Oh, Mike, sorry, go ahead.
No, go ahead.
No, I was just gonna say, yeah, so there's the name list and you do have the gases, and well, aerosols are treated differently depending on what type and what model you're using. If you use chem, for instance, well, both chem and the more comprehensive chemistry have the same black carbon, primary organics, and sulfate emissions. There's a difference for the comprehensive chemistry runs, so YChem and ChemChem for secondary organic aerosols. They are not emitted directly, but they will be just through the precursor gases be produced. So they are different. There's a little bit different complexity and depending on what you do. But else, yeah, Mike has answered the question.
Okay. Next question, are you planning to use ERA 5 as one of the observational data sets used in the atmospheric diagnostic package? Then right now, we are not updating the diagnostic package as is. We are moving to Python, and we are going to include a new observational data set, but this new package is really in this infancy right now, and we don't have really funding to do this effort. Then, yeah, I'm not aware of the data set that we haven't decided yet the data set we will include. But this is the status right now. Okay, then what factors can affect the scalability of dynamical cores? Specifically, why CAM-SE scale better than CAM-FV? Rich, you want to answer this?
Yeah, so CAM-F, the main difference between CAM-FV and CAM-SE that impacts this is the way the grid is set up. So CAM-FV essentially has, quasi-constant latitude and longitude, but of course, as you get towards the pole, The longitude goes down to some tiny value, of course. It goes to 0, the pole. But the problem with doing that is you get a lot of noise with these smaller longitudinal scales, and you have to filter that. And to filter that, basically all the grid points have to communicate, and it's that communication that really kills you, because CAM-SE is quasi-uniform essentially. So the Latin long is just about, of course, it's a cube. It's not quite right, but it's just about the same resolution everywhere. And this does not require this this filtering. And that, if you think about it from a process point of view, the processors that contain the elements within spectral element do not have to communicate globally at all. Well, sometimes they do, but not as frequently as finite volume. So when these processors themselves don't have to communicate globally as frequently, then they parallelize, they scale much better. So if you double the resolution of SE, then you get very good scaling, whereas finite volume, the burden of this called a global gather of the information, just basically makes it scale terribly. So there are other reasons, but that's the main reason.
Okay, thank you, Rich. Okay, next question. Can you account for time variability in the solar cycle or via the eccentricity of Earth's elliptical orbit? If so, how can this time variability be changed?
So the solar cycle is specified in the atmosphere name list via input files, and Wacom has 2 additional ones. CAM has one that specifies the solar spectral irradiance for each wavelength bin versus time. So it has time variability in it, and when you're running a transient run, it has the solar cycle. Wacom also has files for energetic particles and auroral parameters. The Earth's orbital parameters are also changing in the model, and they're specified on a CESM level, I believe. Does anyone want to comment on that?
I think you're right, yeah.
Yeah. Okay. I think we will move to the next question because we have only 8 minutes left. Then how can you alter the invariant species in CAM-Wacom R, for example, N2 or H2? Can somebody answer this? Or I'm not.
You could make them variable species, or if you just wanted to change them, I don't know. You'd have to look in the code somewhere.
Okay. Okay, we cannot answer this one on the fly. Then how is hydrogen escape at the top of the atmosphere set? Can you add in atmospheric escape of any gas for that matter?
Yeah, you could add it in for any gas. Again, I don't know the details, but it yeah, has to do with kinetic energy versus gravity.
Okay. Okay, thank you. Okay, how can you change the atmospheric pressure in CAM-Wacom to say 0.5 or 1.5 bar atmosphere? And if we don't know, we will pass, because I see I have 3 raised and I would like to try.
Well, I mean, CAM has been used for exoplanets, which I think Mars has of order this surface pressure. So it's possible, but I doubt it's a question of just saying PS equals 0.5 bar in the name list. So yeah. We would have to look into that.
Okay. What's the status of CAM-MPAS development? Let's try to stay brief on the rest.
Okay, I'll be quick. Is it me?
Yeah. Yeah, it's you.
So MPAS, for those who don't know, is a model prediction, the model for prediction across scales. This has been developed by another lab, M-Cubed here at NCAR. And we've been trying to integrate that as a dynamical core into CAM. And we're pretty close along the line, far along the line. And I think we have some simulations with simple physics right now. So, and the next step is to do full simulations. I think we're pretty close to that.
Okay, thank you, Rich. Next question, it's about the resolution. Then the question said that right now the highest resolution is 1/8 of a degree. And are we going to develop a global grid with even higher resolution for the atmospheric component? Rich?
Can we do that too? Okay.
Yeah.
So, yes, so that is true. So with 12 kilometers, it depends what you mean by develop. We have done with these, the regional refinement, about 6 kilometers, about half of this, but only in a particular region. With all models, of course, if you can imagine doing a 6 kilometer high resolution model, it is extremely expensive to run, and one has to think about the appropriateness of the parameterization. And a big one is deep convection. So is it a configuration that's appropriate to run with that particular approximation? And so it's marginal anyway. So I mean, the bottom line is no, we're not thinking of developing in a comprehensive sense anything much higher than what you see there.
Okay, thank you, Rich. Okay, then this is the end of the question that was submitted, and I have 3 raised hands. Then the first, I don't know if you still have a question, but there is a Nathaniel Wong. Then if you want to, I'm going to unmute you if you have still a question. Oops. Okay, or you can unmute yourself.
Hello,
okay, yeah.
Can you hear me?
Yeah.
Yeah, actually, I had 1 question, but now I have 2, if that's all right. The first question is related to the 0.125 degree grid, basically the specification of the maximum resolution for spectral elements. So you're saying that it's possible to, go to higher resolution, and but we have to specify it basically, because this would be a custom grid per se.
Are you talking about the mechanics of specifying the grid specifically, as in like the technical aspect of it?
Yeah.
Okay, yeah,
so
I mean, the generation of the global grids is not difficult, at any resolution. I don't do it, but my understanding is, I mean, the complexity comes from how appropriate it is, to run 800 meters or something in a global simulation with the physics that we have that were not built for those resolutions.
Okay. My second question is regarding previously, there was some mention of using Python to kind of using Python in CESM. Is this like some sort of wrapper that is going to kind of replace the process that you have now per se when it comes to specifying parameters and things like that? Is that the purpose of the Python script or the Python framework that you are talking about previously? I wasn't quite sure.
I think that was discussed more in the context of the diagnostics packages. Is that right?
Yeah.
That the new diagnostics packages will probably be in Python rather than NCL, which they're currently in.
Oh, so you're talking about diagnosing the output from the model. Okay.
Yeah, there are various packages that exist where you can just run them on the output and get basic plots, and those are going to be updated probably to be in Python.
I understand. Thank you so much.
Okay, thank you. Okay, then the next question, there is Kathy Lee. Kathy, if you still have a question, I just unmute you.
Hi, thank you. I have sort of 2 questions, but they're related. The first one is, I'm not that clear about what's the difference or connection between the dynamical core and the spatial resolution. And the second one is if I change CAM's dynamical core, how would the compatibility be with other components, say the LANT model? Because I'm not aware that LANT model has this capability to regionally refine. Have I made myself clear?
Yeah, shall I take that one? So there's definitely a definite separation in the model between the dynamical core, which deals with things like advection, horizontal diffusion, certain processes like that, versus the physics. So the thing about the physics is every column is independent in certain respects. So it doesn't matter if you have a globally even number of columns or columns that are regionally refined and very close together. So in principle, the physics does not care. And in the same way, in that grid, the land does not care. So you can have a high resolution land, co-located with your regional high resolution atmosphere. And so on the physics side, doesn't care. And for the dynamics, the numerics just operates at that high resolution, like no problem. So there's no technical problem with the grid per se, particularly with land. There isn't.
Yes, thank you. Okay, then I have still 2 questions. I have 2 raised hands, and then there is a break right now. Then if my panelists can stay a few more minutes, we can go through the 2 more questions. Then Marta is the next question. Marta, I unmute you.
Hi. Yeah, so my question is about the variable resolution atmospheric model. So how do you select the physics and dynamics time steps? Because I guess you would select the smallest time step, but then it would increase the cost of the simulation.
That's me. Yeah, I mean, it's a compromise, as you can imagine. You can run it at a very high resolution; it's much more accurate. But of course, at least obviously double the time step, you double the cost of the dynamical core. So it comes down to keeping this solution stable, essentially, so you don't get spurious gravity waves, for example, particularly around orography, like I think as I spoke before. So there are rules in there in terms of how it should relate to the horizontal grid spacing as well. So but it's somewhat qualitative, just to make sure you suppress spurious noise.
Okay, thank you, Rich. Thanks. Then I have 1 more question, and I'm sorry if I mispronounce your name. It's Hao Fan Lee. Then I have unmute you.
Yes. So my question is also regarding the Python and NCL, the switch. I've been using NCL to visualize the CSM data, the output CSM LE output data. So I've been following the instructions online from NCL. There's lots of guidelines for NCL, but since now NCAR is switching to Python, I'm wondering if there's like documentation available online for how to do the same thing using Python, like the same functions as using NCL before.
I think that's something we all want. I don't know if there's the GeoCat thing, which is intending to do that, but I just had a look when you were talking about it earlier, and it seems pretty, there's not a lot there compared to what's there in NCL.
Mm-hmm.
So yeah, at this point, I don't think there are plans, unless I'm.
A lot of us are still using NCL.
Yeah, I'm slowly trying to learn Python.
We do try to engage everybody who knows Python, like the users, to help us with that as well. Yeah. I mean, maybe over this musical effort, but also over the diagnostics effort, and it is desirable to have, the users help us and design routines and kind of feed them to us as well. I guess we haven't quite set that up, that it's possible, but maybe that would be something desirable. So if you have routines that work and that if you're really good in Python, let us know, and then maybe we add those.
Also, I felt like I've been seeing lots of email just when people ask questions about NCL scripting, and lots of scientists at NCAR, they reply to the email, and then later that back and forth of email will become available to the public. I just wonder if the same type of resource is still available right now. Is there like scientists still running that?
NCL talk, yes,
or
I think
NCL.
so, yeah.
So the important thing to think about NCL is it's still supported for a while. It's just not being developed. So there's nothing new going in there. So there is support. The main way to support is through NCL Talk, which will exist as long as people need it, I think. So it's going to be years, not months, I think. On the Python side, the plan, as Cecile mentioned, the goal with the computational lab here is to have this geocat capability in Python. So these are Python routines, but they were only gonna kind of move across from NCL those things that are not available in Python easily already in another package. That's my understanding. So they're not gonna just move all the same functionality into a Python package. They're only gonna select those things that are highly used and you just can't easily do them in Python already.
I see.
I do think you would be wise to familiarize yourself with Python. I wish I knew.
Oh, yeah.
I wish I had started a long time ago, because it seems like I feel like I'm getting behind. So starting slowly is probably a good idea.
Thank you.
Okay. Okay, I don't see any more raised hand. Then I'm going to thank the panelists again and to thank everybody who was in the session. And I think right now you have a break and then you have some networking activity. Then thank you everyone, and we will see you in the other session. Thank you.
Great. Thank you.
Thanks.
So as Cecile mentioned, so now you have the choice to either stay online and take a break first and meet among yourselves if you'd like to do so. And I would say, in order to know how many of you are interested in doing so, please raise your hands. And depending on how many of you raise their hands, then we can dispatch you in different breakout rooms. And so you can get to know each other a little bit better. Okay, quite a few. So we have 15. So, okay. We can either divide this group into 2 breakout rooms, 7 or 8 people, or 3 breakout rooms of 5.
So Gunter, this is Elizabeth. For this first session, I can just have Zoom randomly assign people to a breakout room, everyone who's online right now, and you can accept that invitation or not, and join that room, and it could be just random this first time around.
Yeah, so the thing is, some people have raised their hands, some have not. So I want to make sure that those people who raise their hands are actually not alone